Hey, welcome everybody to a short video called The Human Pressures on Groundwater. Hopefully you know something about the basics of groundwater flow now. In this video, I want to look at how humans and cities and agriculture place demands on groundwater that might not be able to be sustainable. So I'll again start out with a map of precipitation. Notice that many parts of the United States are a desert. We know this already. In particular, Arizona, Southern California receive almost no precipitation each year, especially in the lowlands. So what that means is that if you have cities or intensive agricultural use in these areas, you're basically drawing out way more groundwater than can be replaced by recharge processes. And that's illustrated by this USGS figure, which shows groundwater depletion in cubic kilometers from 1900 to 2008. So notice that a lot of wetter parts of the United States, the Northeast and the Pacific Northwest, those places that have high rainfall, they're not really depleted at all. But those arid parts of the U.S., the Great Plains and the Southwest, they've lost a lot of groundwater over the last 110 years, and it's not being recharged fast enough. So in this video, we'll take a short look at some agricultural and urban pressures on groundwater, and then we'll talk a little bit about water regulations and how those can be pretty wacky. So, considering agricultural pressures, just think that a field of soybeans requires at least 600 millimeters per year of water. So that's 0.6 meters, that's 2 or 3 feet of water each year. And to put that in contrast, the recharge rate in some parts of the high plain aquifer is 7 millimeters per year. So you'd have to pour almost 100 times more water onto a field of soybeans than you could recharge into the aquifer. So obviously in some areas, agriculture requires more water than can be drawn out of the ground. And that's the core of the problem. Also, agricultural irrigation tends to be somewhat inefficient, although this has improved a lot over the last 10 years. In particular, we see large evaporative losses as water is sprayed onto a hot, dry field. A lot of that water just evaporates immediately. Likewise, some agriculture requires transport of water in open canals or aqueducts, so you get a lot of evaporation off the surface of those irrigation canals as well. So in addition to agriculture, urban areas also place pressure on groundwater supplies. And you always have to ask the question when you're thinking about an urban area, what's a sustainable rate of groundwater consumption? And we've talked about this a bit, but groundwater is really a flow. Groundwater will replenish itself. It will flow from high pressure to low pressure. So it is a flow, and the way to think about this in terms of an urban area is you can probably withdraw some fraction of that flow and consider that to be sustainable, right? And knowing that it's going to replenish itself over time. But of course, that acceptable fraction varies a lot. For example, in Phoenix, Arizona, extremely large city in an extremely dry area. So the demand by groundwater pumping is incredibly intense and the recharge is incredibly slow. In contrast, where we live, Middlebury, Vermont, relatively small town, so the demand is relatively low and the recharge is enormously fast because it's so wet here in Middlebury. So in Middlebury, we basically have nothing to worry about in terms of groundwater depletion. It would be a long time before we were able to meaningfully deplete it. In the southwestern cities, this is a huge issue. So what happens if we pump water out faster than it can be replaced? Well, we generate what's called a cone of depression. And this is illustrated here. We've got our farm field, we've got a water well that's just been drilled. So the water table was doing pretty well. And then suddenly we start pumping really hard on this well in order to irrigate our crops. And we draw that water out faster than it can be replaced. So although yes, the water does flow back towards the area of lower hydrostatic pressure, if that flow is too slow, then you develop a cone of depression and you actually reduce the level of the water table. And in this example, the water table has actually been drawn down so much that it's actually been drawn below the level of this particular well. So that's a problem. Obviously, whatever water was coming out of this well was probably useful to these people. And imagine if these aren't the same people. Imagine if this is your house and this is your farmer neighbor who pumped as much groundwater as he wanted, and that actually caused the water table to drop and run your well dry. Believe it or not, this type of thing happens all the time, especially in the western U.S. So just to illustrate that example, here's a map of the High Plains Aquifer water table elevation. And the elevation of the water table has dropped more than 40 feet over the last 15 years in many parts of the High Plains Aquifer. So these dark red colors are the areas where the drop has been 40 feet in 15 years. That's pretty tough to keep pace with over the long term. It means farmers are going to keep having to drill deeper and deeper wells to continue to irrigate their fields. So we've talked about how one neighbor's pumping might run another neighbor's well dry. So how is this regulated? Obviously, this is going to create a lot of contention, and we're going to need lawyers, and there's going to be a lot of competition for water in the western U.S. So I'll just run by you a couple of the most common approaches to regulating groundwater and surface water. So groundwater, we've got two different common regulations. One's called the rule of capture. That basically means if you own the land, you can pump the groundwater and you have the right to as much as you want. Okay? A slightly more moderate approach would be the reasonable use regulation, where landowners are entitled to some reasonable amount that's adjudicated by the government. So obviously, landowners like to be able to pump that water as much as they want under the rule of capture, but that may have major negative effects which might require a reasonable use regulation instead. So in terms of surface water, a couple different ideas. One is riparian rights. Basically, whoever owns the banks of a water body is entitled to an undiminished flow from that body of water. So if I live on a river, it's guaranteed to me that river should be flowing at some level when it gets to my house, and I should be able to draw off some amount of that water. A use-based approach would be allowing some non-owners of that water to actually use a fixed amount of the discharge. So for example, maybe you're going to sell 5% of the Colorado River's water to Los Angeles. Even though they don't live on it, they're going to be able to use some of that water. And quite often, a prior appropriation regulation will be in effect. So whoever was using the water first is entitled to be able to continue to use that same amount of water. So boy, think of all the problems that are created by these different regulation models. Water is something that flows where it wants to, and there's no guarantee that there's going to be an adequate resupply, particularly of groundwater. So a lot of problems arise here. And in particular, think about what happens when we use the rule of capture to govern groundwater, but then we use a riparian rights approach to govern surface water. Well, we've learned in these videos that groundwater and surface water are connected. So if somebody pumps down a lot of groundwater, that might also affect the amount of river water. It might turn a river from a gaining stream into a losing stream, or it might dry up a spring that feeds that river. So there's a lot of ways that these different regulations can conflict with each other. And I'll just close this video by pointing out that Many urban areas in the southwestern U.S. don't even have close to enough groundwater to support themselves, not even close, or to support their agriculture for that matter. And Southern California is a great example of this. The Los Angeles Basin and Southern California in general get all of their water from an extensive network of canals and aqueducts. For example, the Los Angeles aqueduct drains the east side of the Sierra. The California aqueduct drains the west side. The Colorado River aqueduct brings water over from the Colorado River, all bringing it to agriculture and urban drinking supplies in Southern California. So there's a huge amount of redistribution of water that goes on in the southwestern U.S. And here's just an example of the California aqueduct making its way through the hot, dry plains of Southern California. So in review, we've looked at agriculture and urban pressures, and we talked a little bit about water regulations and some of the conflict that can generate. Here's a couple of concept questions, and you'll see a quiz link below this video. Thanks.